Good evening, everybody. Good evening to you all, and welcome to the Royal Statistical Society, and welcome to the second in our series of 180th anniversary lectures. Those of us who were here last time heard David Hand talking about the improbability principle. Our next one is going to be in June, where we're going to hear Peter Riddle talk about statistics in public policy. But tonight we have a very special lecture for you from David Cox. Now, this isn't his title, and I want to apologise in advance, it isn't his title, Statistics Past, Present and Future, but I think it is fitting. I did promise David I wasn't going to into a great introduction for him, and I don't think I need to, because as I look around the room, there are so many people here who have learnt statistics from David, who've grown up learning from David and understood and interpreted statistics through his wisdom and knowledge. And he is such a towering figure in our profession that I think I don't need to do any more than introduce him by helping us each think about how we first came across David, what we have learnt from him and his work, and particularly to recognise his power to inspire the next generation of statisticians into our profession, which fits us very well for the future. I'm not going to say any more, David, although I'm tempted to. The floor is now yours. David Cox, Statistics Past, Present and Future.
I'm very grateful for this invitation, and I'm grateful also for having the title chosen for me. I was going to point out, when I came to re-look at the title, I did decide there was probably a typing mistake in there, in that it should be history or present position or future, because any of those three is enough to keep us going for considerably longer than we have this evening. Now, I'm going to talk about statistics as it concerns research in the natural sciences, the social sciences, and applied areas that go with those, like engineering, agriculture, medicine, the environment, and so forth. Not about statistics as it concerns, in the older meaning of statistics, official statistics concerning the state, except where those two are but. So I'm going to talk about yesterday, today, and tomorrow. And of course, for the research worker, yesterday can be fairly interesting. Today is what matters. And if only one knew something about the future, that would be more important still. But then, what do we know? So yesterday, history is interesting as long as it's not about who did what first. Stigler's law applies there. Stigler's law, you remember, says if you say X did something first, there's always somebody a bit before X who got a fairly similar idea. So that's not fruitful. But the notion of where do new ideas come from, how they developed, how do they develop in time, why do some things take off and not others, that is intriguing. And then there's another aspect to history that's important. And that's this tension. Scientific research is an intensely personal activity, an individual activity, or nowadays more commonly small groups of individuals acting together. It's an intensely personal thing. And yet the advance of science is a totally impersonal thing. So we have this analogy, I think, of a great wave moving irresistibly forward, the wave of advancing knowledge, but inside that wave there are people going this way, that way, up, so back to competing with one another and so forth. And it's that tension, one aspect of the history is that tension between the individual activity and the broad flow of the subject. And that tension, of course, leads to disputes. And up to a point, that's constructive. It's a sign of the intellectual energy of the field. On the other hand, if those disputes go too far, they can become deeply destructive. And an extreme example of that was the meeting of our society on March the 25th, 1935. And I'm intrigued to say, I'm sure there's nobody in this audience who was there. There might be one or two people still alive who are actually there, although I think it's unlikely. But the occasion is fully recorded in the Society's journal, when there was a massive, massive, massive quarrel. And the destructive influences of that, in a sense, I don't think it's exaggerating to say they can still be seen in parts of the world. I think not so much in the UK, but perhaps in the parts of the United States, one can still see the echoes of that controversy. So if the controversy gets to that level of personal intensity, it can be really very destructive. So I've talked a bit then about the interplay of the personal and the impersonal. When we talk about the role of the individual, I must come almost immediately to the pivotal role of R.A. Fisher, who did many things, but between 1920 and 1930, he had a whole flood of ideas: randomization, factorial experiments, the analysis of variance, sufficient statistics, properties of maximum likelihood estimates, and so on, and other things as well. And these were highly individual efforts, written in a characteristically personal style. But it's very hard to imagine that had Fisher worked in some totally different field, none of these things would have emerged. Surely they would. They were driven forward by the pressures of the applied areas at that stage, predominantly the needs of agricultural science and to some extent genetics. So we have that interplay. I'm not going to attempt to give even a brief history of our subject, but one could go back to the early 19th century mathematicians, Laplace and Gauss, through the 19th century, coming to R.A. Fisher. And then the other, I suppose, major of that period, Harold Jeffreys. Now, when I was an undergraduate, Harold Jeffreys was described as the man who invented the Earth, because in 1924 he'd published a book called The Earth, which is regarded, I think, as essentially the foundations of modern geophysics. And it was the problems of the analysis of observational data in the physical sciences and the challenges that those arose that led him to a number of papers and a book, and then eventually in 1939 to a famous book called The Theory of Probability, which incidentally was first published as a monograph in physics. That was a tiny proportion of Jeffreys' work, but all the same it has and continues to have a really considerable impact. Of course, there were other figures of the period, Carl Pearson, obviously, and particularly Yule and Student. Student was, you probably know, an industrial chemist and eventually an industrial manager. And he didn't write many papers in what one calls statistical methodology, but what he did write illustrated an important point. His mathematics was the mathematics of a first-year chemistry student. But with that relatively tiny amount of mathematics, he was able, when he wrote relatively mathematical papers, to make striking innovations because he saw through to the heart of the problem. There's one other thing I should say about R.A. Fisher. His perhaps key paper was called The Mathematical Foundations of Theoretical Statistics. And notice very carefully the choice of words. Not mathematical statistics, but theoretical statistics. And I think it's important to appreciate that the theory of statistics is not primarily mathematical. It is conceptual. It's about ideas. translating those ideas into something effective may require a bit of mathematics, a lot of mathematics, a great deal of mathematics. In the sense, the more mathematics, the better within reason. And Fisher was, in a certain sense, a very powerful mathematician. Fisher also wrote very beautifully. It was said, I've forgotten by whom, that you had to peruse every sentence carefully, note the position of each comma, and that if anything was unclear in Fisher, it was because he wanted it to be unclear. I don't know who made that nasty remark, but I think there's perhaps a certain element, harsh element of truth in it. Well, where are we today? Well, the most obvious thing today is that the development of computing has meant that simple statistical methods, not so simple statistical methods, complicated statistical methods, can be used in all sorts of different fields, used and misused, often by people who wouldn't claim to be statisticians, but hopefully intelligent users of statistics. And that's something that certainly has to be welcomed. And it was always the case that computation drove what was practicable. Even in my time, when I first began statistical work, there were many methods that were there in the literature of time series, beautiful methods of time series analysis, for example, certain methods of multivariate analysis that were in principle known, but so difficult to implement without driving oneself absolutely insane, that they weren't really all that useful. Masses and masses of time series analysis, of time series data were around, but using sort of standard methods on them was only possible to a very limited extent. But now that's all changed. So the present state of vigorous state of applied statistics, which you see in our journals, but even more so in subject matter journals, which are full of material that 20, 30, 40, 50 years ago you would never have found in these journals. That's driven by computational considerations, surely. I've picked out two particular things for mention, the work of the London School of Hygiene and Tropical Medicine, which for many of us is a kind of physical home of the society. For many years, the main meetings of the society were held there, and one looks back with nostalgia at them. But work there, for example, in training clinicians and other medical research workers in the intelligent use of statistical methods is extremely important in that field. And then by contrast, the beautiful work at CERN leading to the discovery of the Higgs boson, massive experiment, and something like 10 years of work between setting up the experiment, building the very elaborate system that was necessary, and with something like a couple of hundred physicists waiting for data to analyze. And so there was very intensive discussion in a series of international meetings, mostly amongst physicists, but also to some extent amongst statisticians, about how these data should be analyzed when they eventually came. I don't think there's ever been, I'm speculating, but I'm pretty sure I'm right, I don't think there can ever have been an experiment in which so much discussion went on beforehand about what to do with the data when it came. I'm now going to make a number of detailed comments. The overwhelming part of our literature is about the analysis of data. But of course, the design of investigations is crucially important. Experiments, prospective observational studies, retrospective observational studies, simple sampling procedures. Perhaps the theory of those is well understood, but I'm sure there's still much more emphasis needs putting on them, and it's a comment on the fragmentation of our subject, that these four areas that I just mentioned are by and large studied by different groups of people and written about in different journals. And of course, an experiment and an observational study. These are two very different things, and one should, although sometimes it isn't quite as clear-cut as is sometimes stated, but nevertheless they're two different things. But on the other hand, there are strong common links between design issues in all those four fields that I've mentioned. So that's something that I think we should be aware of in our teaching, particularly, because at a purely personal level, I could say there are very few things more satisfying as a statistician than to take part in the detailed discussion of the design of investigation. Analysis formulation, by which I mean, I'm talking about, I should have said this earlier, I'm restricting the discussion for the moment to methods of analysis that are based on a probabilistic model. And that is a severe restriction, which I'll come to later. But then where is that model to come from? How can that model be related to the underlying physics or the underlying biology or the underlying sociology, if there's whatever the intellectual base of the subject might happen to be? And we, leading on to the notion that we normally express our conclusion in terms of parameters, constants that we think of as reflecting important properties of the system that we're studying. An idealization, of course. What's the role of non-parametric methods? Well, I think the broad principle there is if a problem can't be tackled non-parametrically, it's dangerous to tackle it parametrically. But on the other hand, if it can be tackled non-parametrically, it would be better to tackle it parametrically. And think of the competing risk issue, for example. I might have been tempted to spend the whole of the lecture about what's sometimes called the principles of inference, or sometimes the foundations of inference. I think I once heard, I may have imagined this, but I think I once heard R.A. Fisher say, foundations. People think they're propping up a great building. Actually, they're mice scurrying around in the basement. I don't think I've got the imagination to have dreamt that up on my own. But I think he said something like that. Of course, whether he included himself in the... I'm not sure, but never mind. If we talk about foundations, to realize, as in other areas of science, the analogy of a building resting on its foundations is not accurate. It's as much the foundations depend implicitly on what's above as much as what's below. And you see that in other areas. Quantum mechanics, for example, is perhaps one of the great intellectual triumphs of the first half of the 20th century. Beautiful theory, mystical theory that it explains and predicts all sorts of exotic phenomena. But the foundations are in some disarray. And I was very pleased to see in the program for the forthcoming RSS conference in Sheffield that there is a session on the foundations of quantum mechanics. What is the role of probability in quantum mechanics and so forth? And these are very interesting issues. And I'm not saying they're unimportant, but the whole structure of quantum mechanics and its success doesn't rest on them. It may be improved or illustrated by them. And I think much the same is true about the foundations of statistical inference. Unless the foundations strongly interrelate with the varied problems of application, then they're not very effective. And I think of course, the well-known tensions between Bayesian and frequentist methods in this discussion, I think is to some extent misunderstood. I don't see the distinction there. It's interesting also that Brad Efron in Stanford, I think, has written somewhat similarly. It's really more between people who see the primary purpose of statistical analysis as taking data, making assumptions about by a model about its generating process, assumptions that can in principle be checked, and attempting to find relatively objectively, although objective is a dangerous word, relatively objectively what is reasonable to conclude. And both from that point of view, both Fisher and Jeffreys were doing exactly the same thing. And Jeffreys indeed referred to himself once as Fisher's most disobedient student. And and as far as estimation is concerned, very often the answers from their approaches, the Jeffreys invariant prior and so forth, are virtually identical with the Fisherian answers. Where they differ, I think it's arguable that the Bayesian solution has to at least to be adjusted, and people like Bernardo in Valencia have put a lot of effort into trying to do that. And that approach is to be contrasted with the view of people like F.P. Ramsey, the philosopher, De Finetti and L.J. Savage, that statistics is about personal decision-making and personalistic views of belief. Now, from what I've said earlier, it'll be clear I'm in no way whatever dismissing the personal aspects of scientific research. But I think in many contexts at least, the mixing of the relatively objective with the personalistic is confusing to the general outlook, the general reader or observer. It may be very helpful to the individual decision maker. That's an arguable issue. I'm not dismissing the personalistic theory, but I'm putting it in a different box from the others. Another issue that's been around for, of course, centuries, you might say, is the notion of causality, which has received a lot of attention in relatively recent years. In a sense, it was really a massive insight into this was obtained by Fisher's randomization theory of the design of experiments. It was W.G. Cochrane in a paper read to the Society in 1965 who raised the whole issue, how could this be translated into observational studies? And interestingly, I recall this quite vividly, Bradford Hill proposed the vote of thanks to Cochrane and talked about his so-called guidelines from which causality from observational studies is made more plausible than it might otherwise be. And there's been a lot of formal work since then. My colleague, Professor Vermut in Germany, and I have got into some trouble because we, in our writing, have talked about potential causality inferred from the kinds of model that are being suggested. And what we mean by potential causality is that, okay, you're trying to fit a model that represents causality in some sense, and that's an altogether good thing to do in many contexts. But to think that you've established causality, which is a very emotive and deep word, to think that you've established causality from one observational study, say, is misleading, perhaps particularly in the biomedical field, where we see an enormous contrast between studies carried out with enormous care, analysed meticulously and cautiously, the conclusions clearly explained, versus other kinds of study that may get a lot of publicity in the newspapers or on television, which draw strident conclusions, often from either badly designed studies or certainly studies of insufficient size. So I think I defend my friend and I from like particular criticism. I think potential causality is expressing the right note. And it's connected with important notions of generalizability and specificity. How do you know if you've done an agricultural field trial in a particular experimental farm showing this treatment is better than that treatment in terms of yield, or if you've done a randomized clinical trial comparing two treatment all perfectly compliant and so on and so forth, and you find a clear difference. How do you know it applies to another population? The fields in the farm are certainly not a random sample from a well-defined population, nor typically are the patients in a random giving informed consent in a clinical trial likely to be a random sample from a relevant population of patients. How do you draw that? Is the notion of specificity. And that's this issue. Here's a particular farmer placed with what should he do with his particular field, or here's a clinician faced with a particular patient with certain features and medical background and so forth. What is the evidence that the result from this randomized trial is actually useful for this specific individual, which is the problem faced by the individual clinician? And it's only a partial answer to say, well, if you did this, you'd be right 95% of the time, something of that sort. And I think that's to misunderstand the role of things like 5% significance and 95% confidence intervals. They're not typically rules of behavior. Related with trying to improve some notion of interpretability or causality, whatever you like to call it, is the notion that the probability models that we use for our data should bring in, if possible, specific features and be based, for example, on, if it's infectious disease epidemiology, on the simple models of infectious disease epidemiology. And that's an important line of work. Your predecessor as president made distinguished contributions in that direction, and Frank Kelly in Cambridge also, very much so. And in this country at least, this notion that statisticians should concern themselves with stochastic processes and stochastic, who is a very influential figure in our world. Statistical issues, I'm thinking of broader things like, faced with a large amount of data, which we've not, of a kind we've not seen before, how do we start? Do we divide the data into bits and look at it a bit at a time? Do we try and fit some gigantic model to everything? What? And part of the answer to these questions is to try and narrow the gap between what I call analysis and interpretation. Statistical analysis of a set of data would typically consist of saying, we fitted this model, it seems to fit tolerably well. There are these parameters which we hope have a decent meaning. Here are confidence limits or posterior intervals or whatever you like to call them, which tell us how much information we've got about them. That's analysis. Interpretation is, what does it all mean in terms of underlying physics or chemistry or soil mechanics or whatever it might be. And the more you can say, well, that's a subject matter issue, not a statistical issue. But then I don't think that's at all a satisfactory answer. It's important that if we are primarily interested in statistics, that we should try and work to some understanding that will improve the interpretation. In other words, the link with underlying subject matter. And that's related to the causality issue. I haven't said anything. Some people define statistics as decision-making in the face of uncertainty. Now, I stayed away from that, not because it's unimportant, obviously, but there's enough to talk about without going in that direction. And then finally, an important point that I've talked, as I said near the beginning, primarily about statistical analysis that's based on an assumed probability model, which in principle is always subject to some sort of test. Not as, of course, as to whether it's exactly true, because the notion that a model could be exactly true is absurd anyway. But there's no strident misfit between the data and what's assumed. But of course, there are other approaches coming particularly from machine learning and data mining fields, which are much more algorithmic. And parts of statistics are like that. Some parts of multivariate analysis, cluster analysis, for instance, are really more a series of algorithms than particularly based on a probability model. And I think establishing closer links with those lines of work is an important challenge. Now, there are two words that I haven't used, two frightening words for some, two beautiful and challenging words for others. Are you frightened or challenged? Well, I'm frightened, mostly. Well, what can one say about big data? Well, first of all, obviously, there's often a sampling issue. If these are individuals self-selected, there is then a question over what you can reasonably infer. There's the more important issue, or well, not more important, but further issue of data quality. The data at CERN was big data, but it was data of high quality. The data in some big epidemiological and genetic studies are probably pretty high quality. So it's not intrinsically bad, but it's pretty clear that if a little bit of bad data is dangerous, a great deal of bad data is extremely dangerous. So that's an issue. And then there's a matter that's received remarkably little attention in the literature, and that is the assumption really that if you have a lot of data, the precision of any estimates that you get is going to be very high. Yes, I'm talking about sampling errors which go down like 1 over the square root of sample size. So if the sample size is enormous, the formal standard error is likely to be tiny. But is that realistic? Perhaps, and perhaps not. Because all sorts of, not so much distributional assumptions, I don't think that's quite the important, but of hidden correlation and dependence structures in complex data may mean that the standard errors are actually very much bigger. Well, the realistic measures of uncertainty are very much bigger than those calculated by a formal use of elementary methods. And use of things like the bootstrap is not an answer, because bootstrap, at least in its simple form, has strong independence assumptions implicit in it. And then finally, there's the important issue of the challenge of research tradition. The traditional research view is you have a question, or better still, you have some questions. You look to see if you've got any data. If you haven't, you design a study to answer those questions. You then analyze the study and move on. Possibly you may find you answered the wrong question, because as we all know, answering the right question is almost more important than asking the right question is almost more important than answering it. So that's the traditional view. Of course, highly idealized, really. It is a model of the scientific process, not the actuality. But getting big data is the opposite. Collect everything under the sun. Collect information on every time a patient coughs in the United States, in the UK, and send it to some big database somewhere. Is that the right way to do it? And sometimes not. So there's that issue of research strategy. And big data are particularly relevant, as in the case of boson, when you're looking for a needle in the haystack. And there are various versions of looking for a needle in the haystack. In one, perhaps there isn't a needle there at all. What you found is some fiction. And that's the Higgs case, really. Then there's a case where you do know there's a single needle in the haystack, find it and check that you've got it. And then there's the issue, you think there are quite a few needles in the haystack, perhaps 5, 10, 15 or so. Find them and get some assurance you've got the right ones. And this is where the notion of false discovery rate, Benjamini and Hochberg's notion, comes in. Although I think in all those problems, a inverse probability Bayesian formulation is probably more insightful. It doesn't give answers that are very different, but I think it's probably clearer what it is one's doing, although of course, as in all those formulations, rather strong assumptions are needed. Well, I've said a bit about yesterday and a bit about today. Tomorrow, well, I wish I knew. What we have to ask ourselves, there's no doubt at all, there's a ferment of activity in our subject across many areas of application, which is excellent. Are there fundamental ideas being put forward? Well, some. Are they going to be fruitful? Nobody knows. Remember my analogy with the wave. So, are there new things going on? I don't know. Now, there's a general moral that's implicit in quite a few of the things I've said, which is the role of caution for the statistician. It's very easy to be put in the position that you spend a fair bit of time saying to people, well, look, you've done this study, but actually your conclusions don't really follow from it. Either your study design is defective, or the sample size isn't big enough to justify the conclusions you want. And that can be, particularly perhaps in the medical context, a totally necessary and desirable thing to do. But as I said earlier, scientific research is not for the cautious. It's an adventurous process. And so how do we fulfill our role of necessary caution and yet at the same time not go over the top in negativity? And the answer must be something like the balance between what I called analysis and interpretation. The more we can interlink the two, interpretation is more imaginative, more uncertain, is trying to say what's really going on in this problem. The more we can get involved in that side of thing, analysis, almost by definition, have to be quite cautious. But there's, I think, a real challenge there of playing a role of necessary skepticism, but going a bit too far with it. Well, I've talked about yesterday a bit about today, not very much about tomorrow, so I better stop there with that question mark. Thank you very much.
Thank you, David. That was a wonderful encyclopedic review, and the question mark at the end, I think, entirely appropriate. You brought together everything that our discipline has sought to achieve and how each generation has built upon the next, sometimes in a quarrelsome way, sometimes in a complementary and creative way. But your spirit has been about creation and about making sure that statisticians are bold and we are not overcautious when we're faced with the messiness of the world, that we come out and talk to those people trying to interpret, trying to understand and trying to discover things across our discipline. And you mentioned my predecessor, Valerie. I think another mark of her achievement for the profession was really to bring out the diversity that statistics celebrates. And you've reminded us in a very powerful way of that. And that can be a blessing and a curse. It's a blessing because we are involved and connected with everything, but it's a curse because we are spread very, very thinly. David, you've shown us how we bring together the core of our discipline to make a difference in every part of our understanding of the world around us. And you've given us numerous examples from yesterday and today. You've asked us whether we should be challenged or frightened by big data and, by analogy, by the future. Having heard your talk this evening, I certainly feel in the challenge to inspired end of that spectrum, and I think the future is bright for our discipline because of everybody who's gone before us, and particularly because of you, and I thank you very much for your presentation this evening.